Okay, let's unpack this. Welcome to the deep dive. We're here to cut through all that information, overload, pull out the really key insights, maybe some surprising facts, all tailored just for you, our curious listener. Think of it as, well, your fast track to being genuinely clued in on a topic. Today we are taking a very specific, but I think really fascinating journey into the online encyclopedia of integer sequences, the OEIS. We're focusing squarely on OEIS A00259. It used to be known as M2943 and then 11185 for those keeping score at home. This is part of our ongoing series for number theory students, but honestly, it's for anyone who just loves seeing the hidden patterns and, well, surprising links within numbers. Now, the official definition, it says A000259 is the number of certain rooted planar maps. Okay, now, I imagine for a lot of us, myself included, that sounds pretty abstract, right? Maybe complex diagrams. How do we get these exact numbers from something called rooted planar maps? That's kind of the mystery we want to explore today. And to help us navigate all this, we have an absolutely brilliant guide with us. He's a Fields Medal-winning mathematician, really exceptional at taking these complex ideas and giving us the context we need to sort of make it all click.
Well, it's truly a pleasure to be here. You know what's so fascinating about the OEIS, and especially sequences like A000259, is exactly that. You see these mathematical objects that seem, well, completely different on the surface, but then, boom, they're counted by the exact same, often quite simple, sequence of numbers. The OEIS itself is just such an elegant tool, indispensable, really, not just for researchers, but for anyone curious enough to look for connections. And today, yeah, we're going to dive into A000259 and see what kind of surprising links we can find.
Fantastic. So just to give everyone a feel for it, let's look at the first few numbers in the sequence. It starts 1, then 3, then 13.
Then 63, and then 326. Just looking at those 1, 3, 13, 6, 3, 326. What kind of patterns might jump out at you? Or maybe what questions do they raise? So let's jump right into the heart of it then. Unpacking is 0000259. We heard the formal definition, the number of certain rooted planar maps. That phrase, rooted planar maps, it sounds very specific. For those of us not drawing graphs all day, how can we maybe visualize this? Is it like a map where one point is marked as the start or the root?
That's a pretty good way to start thinking about it. Imagine like a network, maybe roads on a map, drawn completely flat so nothing crosses over itself. That's your planar map. Now, if you pick one specific point, maybe an intersection or even a segment of road, and say this is the root, that makes it a rooted planar map. The certain part refers to some very specific rules about the structure of these maps, and this definition, it goes way back. W.G. Brown's work in 1963, Enumeration of Non-Separable Planar Maps, was really foundational for counting these things. But, and this is what makes A000259 so interesting, these same numbers also count something else. Something much more visual, perhaps, easier to grasp intuitively than these abstract maps.
Ah, okay. That's what I was hoping you'd say. So the abstract definition is historically important, sure, but there's another way to see these numbers. So that's where it gets really interesting for me. You're talking about the lattice-path interpretation, right? What does that view tell us about A000259 that the map definition maybe doesn't? Why is that visual link so powerful?
You've absolutely nailed it. The lattice-path view, it just transforms the whole thing. It takes what seems like a very abstract counting problem and turns it into, well, a journey on a grid. Michael D. Wiener pointed this out really clearly in a comment on the OEIS entry back in 2017. He showed that AN is also the number of paths on a grid, using only north and east steps, starting from the origin, 0, 0, and ending at the point 2NN. So for N1, you go to 2, 1, for N2, you go to 4, 2, and so on. And this is powerful because it lets us visualize the combinatorial essence of the sequence. It's tied up in a very specific rule that's not immediately obvious from the map definition. It lets us see the process, not just the final object. But crucially, these aren't just any northeast paths. There are 3 very specific conditions. This is where the certain really comes into focus for paths. First, the path has to start with a north step.
Okay, north first.
Second, it has to end with an east step.
Ends east, got it.
And third, and this is really the key, the defining feature, the path must not bounce off the line y equals 1/2 x.
Right, the no bounce rule. That sounds critical.
It absolutely is. It's what gives the sequence its unique character.
Okay, so what does that no bounce really mean in practice? Let's take N2, where we know the answer is A2 equals 3. Can you walk us through those 3 specific paths that work? And maybe more importantly, show us one that doesn't work and why it's excluded. What does bouncing look like?
Definitely. So for N2, we're going from 0, 0 to 4, 2. With north and east steps, the 3 paths that count are EN, EN, and NN. Let's trace one quickly. Say EN, You go east, east, east.
Mm-hmm.
Now you're at 3 in the arrow. The line y12x is up at y1.5, so you're safely below it. Then north to 3 and 1 north again to 3 and 2. Still below or on the path towards the target point. Finally, east to 4-2. That one works. It never bounced.
Okay, that path makes sense. What about one that's excluded?
Right. Let's look at the path. Een start at 0. Go east to the unknown. East again to 242. Now, take a north step. You arrive at the point 241.
Okay.
Now, look at the line y equals 12x. If you plug in x 2, you get y1. So the point 21 is exactly on that line.
Ah, it touches the line.
Precisely. The path touches the line at 2-1. The next step in een is an east step, 2-1. Since it touched the line and then moved east, which is away from the line in a sense relevant here, we say it bounced off the line at 2-1. So that specific path is excluded. It violates the no bounce condition right there.
I see. So touching it is okay, but touching it and then moving away east in that specific manner is the bounce.
Exactly. It highlights how subtle these combinatorial rules can be. And interestingly, there's a symmetry. These numbers also count paths that start east and north and also avoid bouncing off that same line. It just shows the elegance of the structure underneath.
Wow, it's really quite something how these very precise, almost finicky rules generate these numbers. Which brings me to the next question, naturally. How are these numbers actually calculated, mathematically? Beyond just drawing paths, there must be a formula, right? Maybe one that connects A00259 to other interesting bits of mathematics.
Absolutely. Often, the real beauty is in the formulas they reveal these deeper connections. Michael Wiener, who gave us that clear path interpretation, also provided an exact formula in 2017. It's written as a sum k all man asht 1, k1 c 3 n k knf2.
Okay, that looks intense.
It does, but let's break it down slightly. That c3n nk part is a binomial coefficient. Fundamentally, that's about counting combinations, choosing things. But the really fascinating part, I think, is that fk2. That F stands for the Fibonacci numbers, sequence A00005.
No way, the Fibonacci numbers are in there.
They are indeed. It's not just a coincidence. It points to a really deep connection. Fibonacci numbers often pop up when you have recursive structures or growth patterns. Their presence here suggests there's some kind of recursive way to build these valid no-bounce paths. And just technically, to make the formula work smoothly, we use a slightly extended definition where F1 is taken as 1. It just keeps everything consistent.
That is genuinely surprising. Fibonacci numbers hidden inside these path counts.
And it doesn't stop there. For mathematicians wanting to know how big these numbers get for really large n, there's also an asymptotic formula. Vaclav Kosevich provided one just recently in 2024. It looks like an, 3n plus 12, 5 squared e2, my 3 d2, 21.
Whoa. Okay, that one looks even more complex.
Well, the key thing isn't necessarily memorizing it, but understanding what it tells us. It gives an incredibly close approximation for large n. It shows the sequence grows extremely fast. See that 3n, that's like triple exponential growth.
Yeah.
Very rapid. It shows the power of analytical methods to understand the overall behavior, complementing the exact counting formulas. It's two sides of the same coin, really.
That's amazing. Seeing how you have the exact count maybe tied to Fibonacci numbers and then these powerful approximations for the bigger picture, it also really underscores how collaborative mathematics is, especially within something like the OEIS.
Oh, absolutely. The OEIS is a fantastic example of a community effort. It's supported by donors through the OEIS Foundation, which is crucial, and the sequence A00259 has a history. N.J.A. Sloan, the founder, included it in his original 1973 handbook and later in the big 1995 encyclopedia with Simon Plouffe. More recently, people like Michael de Vlieger have extended the known terms way out, up to N1211 for this one.
1,200 terms. Why extend it so far?
Well, having more data points is incredibly valuable for researchers. It lets them spot patterns that might only emerge later on, test conjectures against more evidence, and just generally provides a bigger laboratory for studying the sequence. And what's really cool is that this sequence isn't just some historical artifact. It's still very much alive in current research. For instance, it pops up in papers like Bounce Statistics for Rational Lattice Paths from Berminger, Gill, and Wiener in 2017, digging deeper into that very bounce condition we talked about. And even in 2024, a paper by Shannon and others, A Partial Recurrence Fibonacci Link, connects it to new findings about Fibonacci numbers.
So it's actively being studied and linked to new ideas right now.
Exactly. It shows this isn't just about cataloging numbers. It's about uncovering ongoing mathematical stories. And, for any students listening who want to get their hands dirty, there are implementations ready to go in Maple, Mathematica, Perry, Magma, Python. It's very accessible to explore computationally.
This has been, well, just a fantastic exploration. We started with these sort of abstract, rooted planar maps and journeyed all the way to these very visual lattice paths with their strict no-bounce rule and discovered they're counted by the exact same, quite fascinating sequence, A00259. It's just a beautiful illustration of how graph theory, combinatorics, number theory, they all weave together around these numerical patterns. And for you, our listener, hopefully this deep dive shows how getting to grips with a sequence like this, its different facets, its formulas, its connections, it's a real shortcut to becoming genuinely well-informed in these areas. You've really gained, I think, a much deeper feel for a truly intriguing mathematical object today.
And maybe it leaves us with a bigger question to ponder, something to mull over after this dive. Seeing these connections for A00259, it really makes you wonder, doesn't it? What other hidden links might be lurking out there between completely different seeming mathematical ideas, just waiting to be found in that vast, incredible resource that is the OEIS?
That is an excellent thought to end on. A perfect question for continued curiosity. Thank you so much for guiding us through A00259 with such fantastic clarity and insight today. And to you, our listener, thank you for joining us on the deep dive. Keep asking questions, stay curious, and keep exploring.